we figured out we are not able to find the propagator. Okay, so there is a problem of figuring out the propagator for the electromagnetic field. Okay, so these things we have already done. Now the point is that, so there is actually this problem arises because there is a freedom in defining the fields. You are having only 2 degrees of physical degrees of freedom for an electromagnetic field, but you describe it by a function or a field function which is having 4 components. Okay, so that means you need to impose conditions on these field functions so that to arrive at 2 physical degrees of freedom. Okay, so we call this choice of defining or fixing the field variable as the gauge conditions. Okay, so there are different ways to put up these conditions. Okay, so let me write those gauge conditions what are usually studied, okay, which are important. So the first condition is the Lorentz gauge. So what is the Lorentz gauge? So it's partial mu, A mu is equal to 0. So you can expand it. So it is simply 1 by C partial phi by partial T plus divergence of A, that's equal to 0. Okay, so these are the different ways to fix A. Clear? समझ आया? Okay. So then you are having the Coulomb gauge. Okay, Coulomb gauge is defined by divergence of A, that's equal to 0, and then you are having the actual gauge. You can do the quantization in any of these gauges. You start with your theory and impose a gauge condition, one of the gauge conditions, and you can do quantization in that gauge. Clear? Okay, let's say if I do with the Lorentz gauge, okay, so if I do my quantization of the field in Lorentz gauge, okay, so the quantization procedure is invariant under Lorentz transform, okay, or it respects the Lorentz transformations. Clear? But we are having the it still gives us the problem of the indefinite matrix, or in other words, the norm of the vector turns out to be negative in this very gauge. You need to fix it more. Huh? Okay, if I start with the Coulomb gauge, if you see the Coulomb gauge is actually is not invariant under Lorentz transformation. That means I can do my quantization in this very gauge. We will see in this very gauge. We will do the quantization in this gauge. I can do the quantization in this very gauge, but I am losing the Lorentz covariance. Okay. Similarly with the other gauges. Okay. You are in the actual gauge like this thing A3. That means that component of the A that's equal to 0. Then you are having another gauge, what we call the temporal gauge. You can mix these gauges as well. There is no problem. So temporal gauge means this phi is equal to 0. Let me write A naught is equal to 0. A naught is phi. Okay, so these are the various gauge choices. Okay, before doing, using these gauge conditions, okay, trying to figure out the quantization in these kind of gauges, what we will do, we will try to figure out the propagator first. Okay, and we will fix the Lagrangian of the electromagnetic field. If I fix the Lagrangian of the electromagnetic field in such a way that I am able to figure out the propagator of the field, then I can say in a given way I can do the quantization of the field. समझ आवा? What my point is that instead of doing directly quantization in these very cases, okay, these kind of problems does not arise in the scalar field. We don't have actually the problem of quantization with the scalar field. Clear? You started with actually phi and figured out its conjugate momentum, imposed the commutation relation. And in Dirac field also you don't have this kind of problem. Okay? So you started with psi and figured out its conjugate variable, imposed the what? Anticommutator. But in case of this field, okay, if you start with, let's say, A, okay, and try to figure out its conjugate momentum, then one of the conjugate momenta is equal to 0. समझा? That means you cannot fix the commutation between A and its conjugate momentum arbitrarily. Okay, you need to choose a specific value of these field variables. समझा? You need to fix these field variables. Clear? समझा? The simple reason being, we are having A is a 4-component vector and I am having only 2 degrees of freedom. समझा? Clear? When you are having 4 components describing 2 degrees of freedom, that means you are having 2 additional degrees of freedom there, is it? So you need to impose condition in such a way that you restrict your domain to only 2 degrees of freedom. समझ आवा? So that your equations are well defined. Okay? Okay, so now let's start with the Lagrangian and try to fix out the Lagrangian for the free electromagnetic field. Okay? And then figure out what is the the propagator. Okay? So let's start. So what is our Lagrangian? So we'll start with the Lagrangian or the action for this EM field. Okay? So what is that? So let's write A. So it's something -1/4 integral d4 of x. Then you are having this f mu. Okay? Clear? So this is the free field. I am not considering the interaction with the matter. So that we can put later on. Okay? So let's rewrite it. So it's -1/4 integration d4 of x. So it's partial mu a nu minus partial mu a mu. Okay? Then you are having partial mu a nu partial. Okay? What I will do, I will simply modify this. First, I will rewrite it in a more suitable form. Clear? Okay, what does that mean? I'll put it in this form. This term multiplied by this term, and another term which is actually a square term. Samasha are the total derivatives which will arise in this formula. Those I want to remove. Okay, you will see in a moment. Okay, now tell me, look here. This is an antisymmetric object. Is this? So this object is antisymmetric in what? Mu and nu. So can I write it like this thing? Twice partial mu a nu. Can I write it? Because what it is multiplied? This thing. So this is antisymmetric in mu and nu, and this must be what? Antisymmetric. So that means you can write this object as this thing divided by 2. So and 2 will cancel. So समझ what I am saying? So this object is multiplying this thing. This is antisymmetric in what? Mu and nu. Then this object must be what? Antisymmetric in mu and nu. Clear? समझ? So when this is antisymmetric, then you can put it as partial mu a nu minus partial mu a nu divided by 2. 2 and 2 will cancel. Aano वापस ले. So that means this I can write as minus half d4 of x partial mu a nu. Then you multiply it with this thing. Partial mu a nu minus partial mu a nu and partial mu. So let's call this as equation. Okay? Clear? So now what I will okay, if you see, this is actually partial mu a nu square kind of thing, is it? But this is not. This partial mu a nu, but nu is here, mu is there. So I want to bring it in the, okay, can you see this as square term? Can you see? Huh? Because this is what? Partial mu a nu and partial mu a nu. This is a kind of square term. I want to bring this as well into a square term. Or in other words, I want to bring it in terms of partial mu a mu square. समझ आवा? Okay, so what? Okay, so let's take this very term. Okay, so let's look at this very term. I am having this term partial mu a nu partial mu a nu. What I will do, I will rewrite this equation in this very fashion. Okay, just wait a second. Just look. So let me take this total derivative partial mu a nu partial nu a mu. Okay, so let's take this very total derivative. What it gives me? Partial nu a mu, partial nu a mu, is it? So then plus a nu partial mu, okay, good, partial nu a mu, is it? So that means this is the term which I require. So it means this term is equal to this term minus this term. समझ आया? Okay. So let's call this as second. So now this objective I want to rewrite this term. Okay. So you can actually exchange the two, partial nu, partial nu. Okay. समझ आया? Okay. So let me write one more term. This thing. So I will write partial nu a nu, partial mu a mu. So this total derivative I can put as partial nu a nu, partial mu a mu, okay, plus a nu partial nu a mu. Can I write it? समझ आया? So this is the term. So these two terms are same. Clear? So now let me use this result in equation 2. समझ आया? So let's write this as third. So therefore, from equation second, we get, okay, what I am doing using equation 3. So we get this partial mu a nu, partial mu a mu, okay. So that's equal to partial mu a nu, partial nu a mu. Clear? So plus for this, what I will write? This term minus this term. So it's partial nu a nu, partial nu a mu, okay, minus partial nu a nu, partial nu a mu. If you see what you have got, partial nu a mu and partial nu a mu. This is actually partial a square. Is it? So this is divergence of a, divergence of a. It means divergence of a square. Clear? Okay. So I need this very term. So have you written it? So write it. So this is minus. So therefore I can write this partial mu, okay, a nu, partial nu a mu. This is equal to two total derivatives like this, partial mu a nu, partial mu a mu, minus partial mu a nu, partial mu a mu, okay. Then you are having this plus partial mu, okay. Let me write partial mu a mu first, then I will write this partial mu. So what I have done here, I have brought this mu down and raised this mu up. Okay? समझ आओ? Now let's substitute this in equation 1. Okay? So using in equation. So what we will get? So this action, that's equal to minus half of integration d4 of x. So the first term will be as such. Okay, so let me put this bracket. Then you are having this minus and this is plus, this is minus partial mu a mu. Okay, so partial mu a mu. Okay, then you are here minus, this minus and minus will make it plus. So plus partial mu a mu, partial mu a mu. Okay, this is minus, sorry, this is plus, this will make it minus, so it's minus partial mu a mu, okay, partial mu. So I have simply rewritten the same original this action. Okay, now if you see, these are two total derivatives. This is a total derivative, this is a total derivative. Okay, total derivative will vanish at the boundaries, is it? So you can apply the Gauss law. So this is actually a divergence of this objective. This is also the divergence of this objective. So you can convert it into the surface integral and extend surface to the infinity. At the infinity, so there are no sources and currents. Clear? So it means this will vanish where? At the infinity. So that means these are okay. So let me write terms second and third. Okay. So above terms. So this and this are total derivatives and vanish at point. What applying here? What? Gauss divergence. Okay. So therefore, what is my action now at hand? So have you written this thing? Huh? So therefore, our action is minus half of d4 of x partial mu e mu partial mu e mu minus then partial mu a mu square. So this is simply a square term. Huh? This is partial mu a mu partial. So when you write the square term, you have to put the another dummy index. समझ आवा? So this is simply a square term. So this is simply what we have done. We have rewritten our original action. It means the problem what exists in this very action still persists. Okay. Now, since we are having a freedom in defining these field variables, okay, what we call as the gauge freedom. Now, let me instead of directly, using the condition on A, what I will do, I will introduce a term in the Lagrangian in such a way it fixes my problem. Okay, or in other words, it fixes my variables. We call that fixing of the Lagrangian as the gauge fixing. Okay, what I mean to say, I will introduce a term in such a way that the problem what exists in the equation of motion for the electromagnetic field gets removed. Okay, so let me tell you how. So let me introduce a term which will fix our Lagrangian. It's actually a non-trivial procedure. Okay, so you have to bear with me. So with the experience, you will understand it actually what exactly it means. So I'll introduce a Lagrangian like this thing. Since this is a Lagrangian, okay. So I'll introduce a Lagrangian, what we call the gauge fixing term. Okay, like this thing. Minus 1 by 2 zeta, okay, partial mu a mu whole square. So that means this very term, what I have put, some zeta, a factor. We call the zeta as a gauge parameter. Huh? Simply what I am doing. Now tell me what I am doing. I am actually keeping a term which actually fixes my Lagrangian. Now, okay, so let's look the other way around. If you see, if I look at the Lorentz gauge condition, in Lorentz gauge, what this object is? What is object is? This object is 0. Clear? Or in other words, if I take, let me take zeta equal to 1. So what I am giving?
Second term.
So what actually I am removing the second term, is it? So it means if I am putting zeta equal to 1, the minus sign is outside, okay? So it means this is a plus sign and I am introducing a minus sign, okay? So I am cancelling out this very term. Samajh aaya? You are getting my point or not? So that means I am introducing a condition in such a way, okay, that it removes the original problem. Okay, you will see it in a moment how it will remove the original problem. Have you got it? What I am saying? I am introducing a term in the Lagrangian that it fixes it. Okay, the term is like this term. Okay, and there is a parameter zeta which we can control. This parameter zeta ranges from 0 to 1. It is having the values of 0 or the values of 1. Samajh aaya? If I take 1, what it says? It cancels actually the second term. If I take 0, it gets infinity. But it's not true. Huh? You will see the result what will occur from here. So is actually a finite result. Samajh aaya? So now tell me what is the Lagrangian therefore. So what is the Lagrangian? Now tell me. So when I write the Lagrangian, it will be sum of these two terms. Okay. So it will be something half of partial mu a nu. Okay. So let me write this in, and partial mu a nu. Okay, then I'm having minus 1 minus 1 by zeta. Can I write it? Okay. Partial mu a mu whole square. Now you are having a Lagrangian at hand. Okay, so this is the free Lagrangian. Okay. So this is the free part of the Lagrangian. Simply it describes what? The electromagnetic field. Okay. Now let me introduce also the coupling with the matter. Okay, so I will write something J mu A. So this is the coupling. Interaction with the matter. Okay. So in other words, I am introducing a source term here, huh? So that I will get a inhomogeneous differential equation. Okay, forget about this term for the timing. So I am having the modified Lagrangian. This is the modified Lagrangian. Okay, so let me put a modified here. Huh? So it is a modified Lagrangian. From this Lagrangian, I should be able to calculate what? Equation of motion. So, samajh how to do that? So our equation of motion is, let me write. So mu nu is already there. Partial alpha, like this. Partial alpha a beta minus partial L by partial a beta. That's equal to 0. Is that true? So you can use this very equation and figure out what is the equation of motion. Okay, so this will be the assignment to figure out the equation of motion. Okay. So let me write it. It is the same thing what we have obtained earlier, but with a little difference. Okay. The equation of motion, what you get, so it is like this thing, minus 1 minus zeta partial mu. Okay, so it is the same equation of motion what we have obtained earlier. So what was the this thing? So this term was not there. Eh? So rest of the terms were there. Eh? So that means 1 by zeta is actually 0. Huh? Huh? So if I put zeta equal to infinity, let's say this term is equal to 0. So it is the same kind of equation what we are having at hand. Eh? Okay? Okay, so now you are having this equation of motion. What is my aim? So I have actually modified the Lagrangian of the electromagnetic field. What is our aim?
Fix this.
Our aim is to figure out what can we still arrive at a propagator or not. Can we derive a propagator from this modified Lagrangian or not? Okay, this is our aim. If we are able to figure out the propagator, that means we have removed our problem. Okay, figuring out the propagator for a field means you are able to quantize that field. समझ समझ? Huh? So we need to figure out the propagator corresponding to this equation of motion. Okay? So let's do that. Let's try to figure out the propagator now. So how to do that? We have to introduce a Green's function, which we call as a propagator. Okay. Okay, so let's start the propagator. What we'll do, so let me write this for you people again. Okay, minus 1 minus 1 by zeta partial mu E mu, so that's equal to G mu. Okay, so this I can write like this thing, G nu lambda, okay, A lambda minus 1 minus 1 by zeta. So this is the term. So then I can write partial mu, okay. So, or in other words, okay, so let me write mu here. Why? So because mu is here as well. So let me write partial mu, that's equal to G. Only mu is free index, huh? Okay. So what it gives me? So you can write the equation of motion like this thing, minus 1 minus 1 by zeta, partial mu, partial mu. It is the same kind of equation we had earlier, like this thing. Only the extra term is 1 by zeta. The same thing. Look here how profound effect this 1 by zeta will have. Okay? So this 1 by zeta will have profound effect. If you see, you can say you are having the same kind of term what we had earlier, but this 1 minus 1 by zeta will change the entire scenario. Oh, समझ आओ? Okay, so okay, so let's define therefore the Green's function. So which implies, okay, so let's define Green's function. Okay, so that is the propagator this way. So how we define G nu mu, this box operator minus 1 by zeta, then you are having partial mu. Okay, so this operator will act on the rank 2 tensor. What will be the rank 2 tensor? What is the index on A? That's mu. So you put a lambda here. So you are having some x minus x prime. So then you put G. What is the upper index? 3 index nu, and 3 index here is lambda, like this. Then you are having delta 4 x minus x. So this is how we define. Okay. Now we will take the Fourier transform. Okay. Take the Fourier transform. Okay. So this is a standard procedure. We have already done it. Huh? Okay. So what is the Fourier transform? So you write this d4 x minus x prime kind of thing as integration d4 of q. Okay, so let me write p divided by 2 pi raised power 4, then e raised power minus I, p dot x minus x prime, then you are having this d mu. Okay, so this is the Fourier transform of d, and what is the Fourier transform of this delta function? X minus x prime, so that's integral d4p divided by 2 pi raised power 4, e raised power minus I, p dot x minus. Now let's substitute it there in this equation. Let's call this equation as 1. Okay. Okay, now let's look here. So this is a box, yes. This is a box operator. Okay. So that means what this box operator is? It is differentiation twice. Clear? So what it will yield? When it will act on, this will be a differentiation with respect to x. It will give me p square. Huh? So twice, I mean minus I. Okay. So let me write it. So it is G nu mu. So it will give me like this minus I p. Let me write alpha. Then again minus I p alpha. What is actually the box operator is like this: partial alpha, partial alpha. First, if this will differentiate with respect to x, it will give me what? Minus I p alpha. Then you differentiate with a partial alpha, it will be minus I p alpha. So that's p alpha square. Okay. So that's minus 1 by zeta. So partial nu will give me what? Minus I p nu. Partial nu will give me minus I p mu. Clear? So whatever the index you are having there, so it will give me that kind of index. Why I have not used it the same kind of index? This is a scalar operator. Okay. So that's why you need actually a scalar quantity here. That's why I have put a different index there. So tell me variable. Huh? Okay. Then you'll write a d mu lambda. Okay. So yes, mu is contracted. Good. D mu lambda. So that's equal to. So this will be p. So that's simply equal to g mu lambda. Okay, so let me write it here. So that's simply equal to. Okay, all the integrals are gone. That I have not written. Huh? So I have taken, because you will be having ultimately this kind of integral d4 of x e raised for this thing and e raised for this thing. Okay. So you take all the terms on one side and the term. So this term multiplied by exponential is equal to 0. So that means this has to be equal to 0. So then you take g on this side. Okay. So what it gives me? So now let's write. So it's minus.
Minus p.
So it is p square g nu lambda minus so it is plus 1 minus 1 by zeta p nu p mu. Okay, then you are having this g nu lambda p, that's equal to g nu lambda. Okay, so now you are having, okay, so this d mu lambda, it's what, a rank 2 tensor. Okay, so we can write, and this will depend on what, the p square term. So last time we have done, so we write this d mu lambda, this I have already told in the last lecture. So as a, anybody, g mu lambda plus b p mu p. Okay, so this is the form of this d. This is the general form of p. We need to figure out what are a and b. So okay, so let's try to figure. Let's sum this thing. So this thing I have already explained. Okay. Okay, let's see. Okay, using equation 3 in equation 2. So what we get? So it is minus p square g nu mu plus 1 minus 1 by zeta p mu. Okay, what is this d mu lambda? So it's a g mu lambda plus b p mu p lambda. So that's equal to g mu lambda. Okay, so let's multiply. So a and b are Lorentz scalars. So let's multiply. So it's minus a p square g nu mu. Then you are having g mu lambda. Okay. Then you are having minus bp square g nu mu p mu p lambda. Okay. Then you are having plus 1 minus 1 by zeta. So a is there. So this a. Then you are having this p mu g mu lambda. Then you are having plus b into 1 minus 1 by zeta p mu p lambda. So that's equal to g nu lambda. Okay, let's simplify it. Okay, let's simplify it. So what this will be? It will be g nu lambda. Okay, so minus a p square g nu lambda. What is the next term? Minus bp square g mu. Okay, mu will be replaced by nu. So it will be something p nu p lambda. This kind of object. Then I am having plus a into 1 minus 1 by zeta p nu p lambda. This very term. This mu will be contracted. It will be replaced by lambda. Then you are having plus b into 1 minus 1 by zeta. So p mu will be there. Then you are having actually p mu is p square. So it will be something p square p lambda is equal to g nu lambda. So let's take g nu on this side. So what I am getting? So it's 1 minus a p square g nu lambda. Okay, let's write this is p nu p lambda. So let me write it in this way. Minus bp square plus a into, okay, so this thing, a into 1 minus 1 by zeta. Then you are having this b. Okay, so look here, it's b. Okay, tell me what it is. B p square, this p square minus b zeta p square. Then you are having p nu p lambda, that's equal to 0. Okay, so this b p square, this cancels. Okay, so now you can compare, because these two tensors are linearly independent of each other. This is a rank 2 tensor, this is a rank 2 tensor. They are linearly independent of each other. It means the corresponding coefficient must be equal to 0. So which implies therefore 1 minus ap square is equal to 0, and a into 1 minus 1 by zeta minus b zeta p square, that's equal to 0. So let's calculate a from here. So a is equal to 1 by p square. Okay, so that means I have got a. So let's use, so which implies a is what? what is b here? So you can have minus b zeta p square, that's equal to minus a into 1 minus 1 zeta. So it means b is equal to a into 1 minus 1 zeta divided by zeta p square. So what is a? Use a. So a is 1 by p square, so it is 1 by p raised by 4. So it's something like this. So zeta is this. So it should be 1 by zeta. It is 1 by zeta. So this is 1 by zeta. E by zeta. So it is 1 by zeta. So what is a? A is 1 by p square. So it will be simply 1 by p raised by 4. So zeta minus 1. And it's something. B is equal to minus 1 minus zeta divided by p raised by 4. Okay? So that means we are able to figure out A and B exactly. Samashya, when A and B are figured out exactly, it means propagator exists. So what is the form of the propagator? Now, so we are able to figure out what? The propagator. So what is our propagator? G mu lambda P. So in the momentum space, so it is A G mu, okay, so G mu lambda plus B P mu E lambda. So what is that equal to? So what is A? 1 by P square. So it is something G mu lambda by P square. So somewhere minus, we are having a minus problem somewhere. Ah, yes. So when you take this G on that side, it will also give me a minus sign, is it? So when you take this G, it's a positive. When you take it here, it's a minus. So it's minus G mu minus this thing. So it's plus here. So it's plus. So it's minus thing. Huh? So it just. So it will be like this. A is a minus. Huh? So it's minus 1 by B. So it will be plus. B is something. 1 minus zeta by p raised by 4 p mu p lambda. Okay, so you can take it like this and take minus out. Okay, so you and take p square out. So the first term is g mu lambda. So it is minus 1 minus zeta by p square p mu p lambda. Okay, so now, so this, okay, we are able to figure out the propagator. Now to avoid the poles at p equal to 0, so you use the Feynman prescription, is it? So this is simply the Green's function. So I can write therefore the Feynman propagator. Feynman propagator means what? So you remove the singularities at p equal to 0. Because at p equal to 0 you are having the poles, is it? So much of the way we have removed the singularities in the propagator for the scalar function, scalar field and the Dirac field, remember? So using the Feynman prescription. So which I can write like this thing, minus 1 by p square plus I epsilon. So this kind of prescription, it is g mu lambda minus 1 by. So one important point is that, okay, so our any physical quantity what we are trying to calculate for a given process, so it does not depend on this gauge parameter, okay? So it's independent of the gauge parameter. Gauge simply means choosing a coordinate system. You are choosing a coordinate system such that your action is well behaved. So much, the way we are doing a coordinate transformation actually in the general relativity, you can think those are the same things. So you are having those Christoffel symbols, we call those as affine parameters. They have the same kind of significance as these A. I mean the fields here. So much, we'll see it in the next lecture. Okay, so this is the propagator for the electromagnetic field. So that means we are able to figure out. So this zeta fixed our problem. Now let's take, if I take zeta equal to 1, we call it as the Feynman to Hook gauge. Okay. Okay. So if I choose zeta equal to 1, so therefore I am having g mu as g mu lambda by p square plus r epsilon. Okay, so this is known as the Feynman to Hook gauge. if I choose zeta equal to 0, so we call this as the Landau gauge. So what is d mu nu here? So it is something minus 1 by p square plus g mu lambda minus p mu p lambda by p square. So this is the propagator in the Landau gauge. Okay. So now let's take this product. So if I take in the Landau gauge this p mu, so let's contract mu. So like this. Let's take the scalar product of p. The momentum 4 vector with this propagator. So let's check it what it gives me. So forget about this epsilon for the time being. So it's minus 1 by p square. Okay, because this is a scalar quantity, then you are having this p mu g mu lambda minus p mu p lambda by p square. Okay, so what this object is? Minus 1 by p square. So this will be simply p lambda minus p mu is p square. Then you are having p lambda, then you are having p square. This is equal to 0 because p square cancels p lambda. So this is a very important condition. P mu lambda p. So this is equal to 0. Okay. समझ आओ? So this is all about the propagator. So let's go to the. So how much time is time? Okay, let's